here's a subset of the vector space P3R. What is P3R again? It's a set of polynomials of, huh? What? What?
Is it 3 terms?
No, it's not 3 terms.
Oh, degree.
Degree 3 or less. Okay, so this is a set of polynomials of degree 3 or less. Okay, so how many terms can this have at most?
4.
4 terms. Okay, yeah. So that's a bit deceptive. Like if you see 3, you might think, oh, that must have dimension 3, but no, this one actually has dimension 4. Okay. So that's something that messes with a lot of people, makes it confusing. Okay, so just make sure you know what this is. So this is a subset where p prime of 1 is 0. In other words, if you differentiate, this prime means derivative, okay? So if you differentiate and plug in 1, you get 0. So if you collect all the subsets of this, which has this property, then you first have to show that V is a subspace of P3R, and B, find the list of 3 polynomials that span V, and then the last one is, can there be a list of 4 polynomials in V that is linearly independent, okay? So, as I said before, if you have a question that says you have to show such and such is a subspace, you now have 2 different strategies. One is to show that 0 is included and it's closed under vector addition and also scalar multiplication, or you can just do everything in one shot by just showing that if you take 2 elements in here and take any random C, then U plus CV is in that subset again. If you show that's done. Okay, so let's say suppose Px and Qx are 2 polynomials in V. Okay, so you have both P prime of 1 is 0 and Q prime of 1 is 0. Okay, and C is any real number. Okay, then let Rx be the thing that you want to show. Px plus C times Qx. What's our goal? I want to show that Px plus C times Qx, is in this V. And then let me ask a totally separate question. Is this polynomial in V?
It's a differentiation of P prime 1, so it should be 0.
Okay, so if what are you trying to say? If I say this is f of x, what are we trying to check?
If it's a
F prime of x, what's that?
when x is 1,
No, what is f prime of x? Give me f prime of x, what is it?
that's x minus 1.
Okay, so what?
If x prime of x is 1,
If you set x as 1, then
prime of 1 is then
1 minus 1, that's equal to
that's equal to 0.
0, then what?
So that's proof that it is in subset of
That
subspace
means
of
f of x is in V, right?
V, yes.
Why is that? Because that's what the definition is, right?
yes.
V is a subset of P3 that has to satisfy this. This is the criteria to see whether something belongs to V or not. Right? Is that good? Yeah. So I think whenever you see some definition, you guys are lazy. Okay? Why do I say that? Because you never bother to think about what it means. you have to think about what it means. What does p prime of 1 equal to 0? In order to answer that question, you should think of an example. You get that? Okay. See, some of you are sitting in here actively trying to listen and you take notes and you think that's everything, right? And you can't be more wrong. Okay? You can be doing all that and still be really lazy. You might be lazy in your mind because you see something and you never bother to ask yourself whether you really understand what that means or not. Okay? And apparently, because nobody was able to answer my question, it means that you guys are lazy. You haven't been thinking about what this condition means. All right? Okay, so now that you understood what that meant, how do we show that Rx is in V?
So that means R prime of
You have to think about what R prime of X is. So let's see what R prime of X is. R prime of X is
P
P prime of X plus
C
C times
Q prime
Q
of X.
prime of X, right? That's like if you're given a question like that on calculus, you would do exactly that, right? So you do that. Now what do we compute?
Now the computer X is equals 1.
X equals to 1. You plug in 1 into X, right? That gives you P prime of 1 plus C times Q prime of 1. What is that equal to?
That should be equal to 0. Or
P prime of 1 is what? We have it, right?
Yes.
0 plus
Plus C,
C times
0,
0, so that's equal to 0.
0.
What does that mean? This implies that
Rx
Rx is in V. Okay? And then we're done. Okay, so just showing this belonging to V shows that it's a subspace. So here's another exercise, trying to show that it's a subspace by checking the three things separately. Okay? See that if the 0 is in V, and then if you have two things, adding them will still satisfy that, and then any constant multiple still belongs there. So show those three things. See if you can do the same. Okay? So that shows part A. Okay, now let's see. Find a list of 3 polynomials that span V. Well, so here, sometimes in math, you can show something very elegantly. You don't have to have your hands dirty. You can just say something in an abstract level, and you don't have to go down to the details. But when it comes to constructing explicitly 3 polynomials, you do have to get your hands dirty. And what I mean by that is you have to explicitly think about what are all the elements in here. So can you tell me a third-degree polynomial in general? How do you write a third-degree polynomial in general? What do you write? The most generic third-degree polynomial. What is that?
ax cubed
Ax cubed,
bx squared.
bx squared, cx plus d. Okay? Now tell me what it means for p prime of 1 equals to 0. I'll give you some time to think. What does it mean for p prime of 1 equals to 0? And you do want to have your hands dirty. In other words, you want, just staring at it, it's not going to work. You have to do the calculation, right? So you have to calculate the derivative, you have to plug in 1, you say equal to 0, you have to see what it means. Okay? Only after that, you're going to see what's going on.
Where is X is equal to 1.
Right, that has to equal to what? That value
That
has to equal
value
to
has to equal to 0.
0. Yes, that's exactly the thing, right? So you get p prime of x equals to 3a x squared plus 2bx plus c, and then p prime of 1 equals to 3a plus 2b plus c, and that has to equal to 0, which means that c is equal to negative 3a, negative 2b. Okay? So now we have a generic formula for any polynomial that belongs to v. And these are, if I plug that in here, we see that if px is in v, px must look like the following. It has to be a times x cubed plus b times x squared plus negative 3a minus 2b x plus d. That's the most generic one. Anything that belongs to v must look like this. Now, can you rewrite this as a linear combination of 3 specific polynomials? That's the next challenge. Can you do that? You have to think about, it has to be something times some polynomial, something times some polynomial, plus something times a polynomial, because it said 3 polynomials, okay? And I want specific polynomials. What could those be?
So it's first one's a.
Okay, a times what?
X cubed minus 3x.
Okay.
Second one's a b. So x squared minus 2x. And plus d. D is
Times.
also,
Times what? 1. Is 1 a polynomial?
yes, it is.
Yes, it is. Yeah. Done. Right? Same as that. Okay? You see what we did? I multiplied this out, right? And then I factored by a. I grouped the terms that had a together, factored the a out. And then I grouped these two together, I factored the b out. And I grouped this one, factored the d out. And now what do you have? Oh, these are 3 polynomials. Each one of these belong to v. You can check. If you differentiate this and plug in 1, you get 0. If you differentiate this, plug in 1, you get 0. If you differentiate, of course, if you differentiate a constant, it's 0 already, okay? So all of these individually belong to v, and anything in v can be written as a linear combination of these 3. Okay, so done. That's the answer to b. Okay, so what we just have shown is that v is the span of these 3 polynomials: x cubed minus 3x, x squared minus 2x, and then 1. Okay, so now c. Can there be a list of 4 polynomials in v that is linearly independent? What do you think? This has to do with something that we proved at the end of last lecture. Can there be a list of 4 polynomials in v that is linearly independent? Are these individually linearly independent? Well, if you set this equal to 0, then if you rewrite it, that means this is equal to 0. For this polynomial to be 0, the 0 polynomial has to have every one of these as 0, right? The only way that this could be 0 is when a is 0, b is 0, and d is 0. So you see that these 3 polynomials are indeed linearly dependent. Okay? Again, we haven't learned basis yet, but if you have the concept of basis and dimension, you have a lot more leverage in knowing what's going on. Okay, so seeing that these 3 are linearly independent and it spans the entire v, that means v is dimension what? What's the dimension of v? It's made of 3 vectors, so the dimension must be
3.
3, yeah. Why do you hesitate? It's obvious. Okay, if something's obvious, say it. Okay, right, so it's dimension 3. Okay? So if you have a dimension 3 vector space, can you have 4 linearly independent vectors inside dimension 3? What do you think? So let's step back and ask this question. On a plane, can you have 3 different linearly independent vectors? Linearly independent means that they're pointing to different directions, right? And you can't express one vector as a linear combination of the other, right? Okay, so if 2 vectors are linearly independent, that means they're pointing to different directions. If you have 3 or more that's linearly independent, that means none of one vector is a linear combination of another. But if you have a plane and you have 2 different distinct directions, then any other vector can be represented as a linear combination of these 2 vectors, right? So in dimension 2, you can't have 3 linearly independent vectors. In dimension 3, can you have 4 linearly independent vectors? No way, you can't, right? Because what's dimension 3? You have 3 distinct directions, right? Yeah. And then any other vector that's in dimension 3 can be represented as a linear combination of these 3 x and y and z axes or something like that, right? So that's the intuition behind it, but we actually have a theorem that we proved at the end of last class. Now, I give you permission to look at your notes. I yelled at you for not thinking, but rather looking at your notes, but this is the time to look at your notes, okay? So look at your notes and find a relevant theorem that we proved that's relevant to this one. Tell me what it is. You have to use the fact that length of linearly independent list is less or equals to length of spanning list. See, these 3 vectors span V. So if there's any linearly independent list inside V, then their length can be at most 3, because we found length 3 spanning list. Okay? So that was the theorem that we proved at the end of the lecture last time. Therefore, using that, since this right side is 3, this is a contradiction. See, we want length 4, right? 4 polynomials. So this will be 4, and we're saying 4 has to be less or equal to 3. That's a contradiction. So, no. Okay, that's how you explain. So if you are to explain, I'll ask to explain as well, then you must quote this theorem, okay? And I need you to have this theorem ready to be quoted.